Hey everybody, the purpose of this video is to help you through a solution to question 4.15.20 in the Collaborative Statistics textbook. This is an interesting one because in it I tell you to not actually do any of the problem except to tell me why it's not binomial. Okay, so if you read it, it says, suppose the chance that an adult in America will watch the Super Bowl is 40%. Alright, so the chance that they watch the Super Bowl is 40%. Alright, which means the chance they don't is going to be 60. Cool so far? Cool so far. So it sounds binomial. I mean, you either do or you don't. It's 2, right? Each person is considered independent. Still sounds binomial to me. Fixed probabilities, independent. We are interested in the number of adults in America we must survey until we find one who will watch the Super Bowl. Still sounds kind of binomial, right? Now I'm going to over-answer this question, and this will hopefully help you understand why it's not binomial. So let's say, okay, this is x equals number of people that we have to survey until we find someone who will, until we find someone, a Super Bowl watcher. Okie doke. Alright. This is going to be the probabilities over here. So we're going to build a little t-table here for us. So obviously we have to ask one person at least, and it's going to have to start with 1, which is a little bit different than the binomials, right? So that's kind of strange. We've been starting with 0 with binomial mostly, but that's not a deal breaker yet. And let's say it takes us one person, and that person watches the Super Bowl. Well, the chance that's going to happen is 40%, because 40% of folks watch, and if we happen to grab one that does, it's a 40% chance that it happening. Done. Suppose it takes 2. You'll ask yourself, what does it mean to have to ask 2 people to find someone that watches the Super Bowl? Well, it means that the first person didn't, which means you had the 60% chance first, and the second person does, which means you have a 40% chance second, which would be 0.24. We'll come back to that. Good so far? Awesome. How about if it takes 3 people? Well, that means the first person that you asked said, no, I don't watch it. Second person you asked said, I don't watch it. And the third person that you asked said, yeah, I do. So now it's going to be 0.6 squared times your 0.4. And hopefully you're going to start seeing a pattern now. You're going to have, if it takes 4 people, that means you have to ask 3 that all say no, and the last person says yes. If it takes 5 people, you're going to have to ask 4 people that say no until the last says yes, and so forth and so on and so forth. And hopefully now you're starting to see why this isn't binomial. In all the binomial distributions that we've been looking at, we've had a minimum value, which has usually been 0, and we've had a maximum value, which is going to be the number that we've selected. The problem with this is, this thing goes off infinitely. There is no top number. I mean, theoretically there's a top number because we could ask everybody in America. But realistically speaking, there is no top number. I mean, in all honesty, this is like flipping a coin and saying you can stop flipping the coin when you flip tails. Okay? So just keep flipping. Theoretically speaking, you could flip that coin forever. You could keep getting heads and heads and heads and heads and heads, but realistically it's going to eventually flip tails. Well, realistically, theoretically, whatever, there's no top number on this distribution. I mean, you can think of it as being n, but the trick with that is, this is now a variable expression, n minus 1 times 0.04. Now what's cool about this is mathematically that still sums to 100%. I'll show you why in the next video. So the probability of x column does sum to 100%. But the fact of the matter is this isn't binomial because there's not a fixed number of trials. This bad boy is actually called a geometric distribution, which is actually a really, really cool distribution. It's the one they use in, say, for example, a plant that's building a manufacturing pieces for a car. You've got a robot arm that's coming in and placing a door on a car, for example, and it gets a certain number of tries until it gets the job done. And if it doesn't, say it takes it 4 tries to get the job done and it misses it, it's going to make the car's going to move on and have to deal with that. So the geometric distribution is great when you don't want to fix the number of trials, but in this case we do because we're talking about the binomial distribution. So anyway, that's an over-answered number 20 for you, and hope that helped.